Okay, now we actually prove this result, or explore this result for a symmetric matrix, a matrix that's the same above the diagonal as below. So that matrix could have the form, instead of A, B, C, D, we'll call it A, Q, Q, D. Just same letter here as we have here, the same number will go here as here. Then, how do we solve the eigenvalue problem? Remember, that's a problem AV equals some multiple of V. Multiple being lambda gives us the equation A minus lambda I times V equals a zero vector, so that the determinant of this matrix, this A minus lambda I matrix, has to be zero. If it wasn't zero, then the matrix would be invertible, and V would be the inverse matrix times the zero vector, be the zero vector. That wouldn't be an eigenvector because it has to be non-zero. So, determinant has to be non-zero. Determinant has to be zero. Well, determinant of this matrix is, you can easily calculate it, it's A D minus Q squared. I'm sorry. A minus lambda I is A minus lambda Q D minus lambda, and you can verify that the determinant of that matrix is what we have here. Very straightforward. Okay, then, does a solution to this equation exist? Because this is a quadratic equation. If the quadratic equation doesn't have a positive discriminant, you can't solve it. Well, the discriminant is your b squared minus ac, where a is the coefficient of lambda squared, b is the coefficient of lambda, and c is the bare numbers that you have left over. In this case, and if we just quote the quadratic formula, the part under the square root is the discriminant, and b squared is going to be quantity a plus d squared. Officially, it's the quantity, negative quantity a plus d squared, but that's the same as a quantity a plus d squared, as I hope everybody's completely aware. And then minus 4ac. Well, a in this case is 1, and c is this, so it's going to be just 4 times this. And that's a squared plus d squared minus 2ad plus 4q squared. Now, that's your discriminant, and it comes out this. And this is going to be positive unless a equals d and q equals 0, in which case it's 0. Either way, it's not negative. So if you have a symmetric matrix, you never get a negative, so you are going to have eigenvalues. As long as neither of these conditions, you're going to get 2 independent solutions. If a equals d, that is, these numbers are the same, and q is 0, then you're going to get repeated solution. Okay, you're going to have a quadratic with 2 solutions, both the same. The solution for negative b plus the square root of b squared minus 4ac, all that divided by 2a, is the same as if you had a minus the square root. And then you have to deal with that. But right now we're just going to assume you have 2 independent solutions, so we don't have to worry about that. Just to give you the general overall picture. So, now if a vector v is of this form relative to the standard basis, that is, if in R2 these are the coordinates of your vector, then how would you represent the vector relative to the eigenvector basis? Well, if the eigenvectors are v1 and v2, then your eigenvector basis is the set v1, v2, and c1, c2b means c1 times v1 plus c2 times v2. It doesn't mean the point with coordinates c1 and c2. It means the point that you get to by multiplying the first eigenvector by c1 and the second eigenvector by c2. Okay, so there's your c1, c2 relative to the basis b. How do you get that? Well, it's pretty clear that this matrix equation, well, that setting this equal to this means that c1 v1 plus c2 v2, that's what this means, is equal to x1 x2. So we have this equation, and gives us a matrix equation, V1, V2 times the C1, C2 column vector equals X1, X2, so that C1, C2 is V1, V2 inverse times the X1, X2 vector, and the V1, V2 matrix, which is, of course, just the matrix whose columns are V1 and V2, the matrix of your eigenvectors. Call this the eigenvector matrix if you like. That's equal to P inverse times X1, X2, where P is the eigenvector matrix. P is this matrix, this is P inverse, and your C1, C2 is equal to this, so that your eigenvector basis, relative to your eigenvector basis, the matrix that you would multiply by your standard basis representation is just the inverse of your eigenvector matrix. Okay, so now I've written something down here, and I'm not even sure why I wrote that down, but I mentioned it. Never mind, I'm not going to mention it just yet. Okay, now if we depict a typical transformation represented by matrix A relative to the standard basis, we have V represented relative to the standard basis, in other words, just the coordinates. We multiply that by the matrix A, and we get the transformed vector AV with respect to the standard basis, because A is the matrix relative to the standard basis. It's the matrix we multiply by this vector to get this vector. Now, if we want to express this in terms of basis B, the eigenvector basis, assuming there is an eigenvector basis, what do? Well, we multiply this vector, that would be our X1, X2 vector, by P inverse to represent it in terms of basis B. And then we multiply that by some matrix C, which won't be the same as the matrix A, but it will be what we call similar to the matrix A. We don't know yet what that matrix C is, but we multiply this by some matrix C to get the vector CV, still with respect to the eigenvector basis, because C is the matrix that works when V is represented in the eigenvector basis. And once we get that, then we can use the P matrix to bring us back down to the standard basis. Okay? P inverse takes us from the standard basis to the eigenvector basis. Its inverse P takes us from the eigenvector basis back to the standard basis. And you can see that in this equation. Okay, so that A times Vs is going to equal what? Well, it's going to be I always have to think this through because I want to think it backwards, and I'm sure you do too. What do? We start with Vs, apply the inverse matrix, apply the C matrix, then apply the P matrix, and we get what we would get if we just did A. So that A times Vs is equal to, well, we start with Vs, we do P inverse first, we do P inverse Vs, then we do our C matrix, then we do our P matrix. So that A Vs equals P C P inverse times our vector V relative to the standard basis. Well, we can then multiply both sides of this equation by P inverse, well, okay, a couple of steps. We start by multiplying both sides of this equation by P inverse. The P inverse will match up with the P, we'll have P inverse A. And I didn't do that, that's not what I did here, so forget what I was just saying. We simply can say then, since A equals PCP inverse, since A times Vs equals PCP inverse times Vs, for any Vs, A must be PCP inverse. And it follows, and I didn't write it down here, but it follows, the flip side of this is that if we multiply, as I was saying before, if we multiply both sides of this equation by P inverse, the P goes away. And if we multiply it by P on the right, we get P, and this is straightforward, but I guess I'd better write it out. So A equals P, C, P inverse. So P inverse A has to equal C times P inverse, because multiplying this on the left by P inverse matches up P inverse with P, giving us the identity, so that we just have C P inverse. And of course we have the P inverse A here. Then how do we get rid of the P inverse? We have to multiply on the right by P. So we get P inverse A P equals C times P inverse P, but P inverse P is the identity. So if A equals this, then this is your matrix C. So if we know the matrix A, and we then multiply that matrix by P inverse AP, where P is the column of eigenvectors matrix, we get the matrix C. Okay? So there's how we calculate C. And the big deal now is, if B is an eigenvector basis, this matrix C will be diagonal. And not only that, it'll be diagonal, and the numbers on the diagonal will be your eigenvalues. The eigenvalues that correspond to the eigenvector basis in the same order, and you'll work that out. This is a big deal for a couple of reasons. One, C times C1 V1 plus C2 V2, where V1 and V2 are your eigenvectors, is clearly going to be lambda 1 times C1 V1 plus lambda 2 times C2 V2, because C matrix times V1 is lambda V1, and C times your V2 vector is lambda times your V2 vector. The other thing is, it's really easy. For example, if we wanted to calculate the 78th power of the A matrix, that would be a big mess. Just think of calculating a matrix times itself, times itself, times itself 78 times. Even if you shortcut that by doing it by itself to get the second power, multiplying that by itself to get the fourth power, and then subsequently getting the 8th, 16th, 32nd, and 64th powers, you'd still have to use 3 of those to get your 72nd power. 2 of those give you your 72nd power. But doing this, you just have to take the 78th power, whatever it is, of each diagonal element, and then use this to transform back to the 78th power of your A matrix. Okay? That could be a big time saver. There are lots of reasons that you want to do this, and much deeper and more profound reasons than those I've just mentioned. So it's a big deal to get that.